Our universe is expanding, and we have no idea why. This simple fact unravels everything we think we know about reality. You are about to journey through 25 of the most profound mysteries in modern cosmology, questions that challenge the very foundation of physics. By the end, you will understand the greatest unsolved puzzles about cosmic expansion, from the enigma of dark energy to the possibility of other universes. We will explore why the expansion rate is a source of bitter conflict among scientists, and whether time itself might be an illusion. What cosmic question keeps you awake at night, staring into the starry abyss? The very fabric of space is stretching apart, and the force driving this is the single greatest puzzle in all of cosmology. We call this force dark energy, a name that perfectly captures our profound ignorance. Its discovery was a complete shock to scientists. In the late 1990s, two independent teams were observing distant stellar explosions, known as Type 1a supernova. They used these explosions as cosmic mile markers, expecting to measure how much the universe's expansion was slowing down over time due to the pull of gravity. Instead, they found the opposite. The most distant supernovae were fainter than predicted, meaning they were farther away than anyone thought possible. The expansion of the universe was not slowing down. It was speeding up. This was like tossing a ball into the air and watching it fly away from you faster and faster, defying gravity itself. Something was actively working against gravity's pull, and that something earned the name dark energy. The leading and simplest explanation for this bizarre effect is something Albert Einstein conceived of a century ago, then later called his greatest blunder. He introduced a fudge factor into his equations of general relativity, a repulsive force he called the cosmological constant. This was a fixed energy density, an inherent property of the vacuum of space itself. Empty space, according to this idea, is not nothing. It has a faint intrinsic energy that pushes the universe apart. If this cosmological constant is real, it means that every cubic centimeter of the vacuum, the space between galaxies and even between the atoms in your body, contains a tiny, constant push. The problem is, when physicists try to calculate how strong this energy should be using our best theories of quantum mechanics, they get a number that is catastrophically wrong. Their prediction is off by a factor of 1 followed by 120 zeros. This is not just a small error. It is the largest discrepancy between theory and experiment in the entire history of science. So what is dark energy truly? Is it Einstein's cosmological constant, a simple but deeply perplexing feature of empty space? Or is it something far more dynamic and strange, a new kind of energy field that changes over time, which some theorists call quintessence? Perhaps our theory of gravity itself, Einstein's magnificent general relativity, breaks down on the vastest scales of the cosmos. The true nature of this mysterious energy, which makes up about 68% of the entire universe, remains utterly unknown. It is the dominant component of reality, and we have no idea what it is. This mysterious dark energy does not just shape the present cosmos. It holds the key to our ultimate destiny. The fate of the entire universe hinges on the true nature of this enigmatic force, leading to several profoundly different endings. One possibility is the Big Freeze, a slow and cold death. In this scenario, dark energy acts as a constant, gentle push. The expansion of space continues to accelerate, carrying galaxies away from each other forever. Over trillions of years, stars will burn through their fuel one by one until the last star flickers out. Galaxies will become dark, cosmic graveyards. Eventually, even black holes will evaporate, leaving behind a vast, empty, and ever colder universe, where no new light is ever created. This is a future of eternal, expanding darkness. But what if dark energy is not constant? What if it grows stronger over time? This terrifying possibility leads to the Big Rip. Imagine the repulsive force of dark energy becoming so powerful that it overwhelms every force in the universe, even the forces that hold atoms together. First, galaxy clusters would be torn apart. Then, individual galaxies. As the force intensifies, stars would be ripped from their solar systems. Planets would be shredded. In the final, horrific moments, atoms themselves would be torn asunder, and the very fabric of spacetime would be ripped apart. The universe would end in a violent, catastrophic singularity. There is a third, more cyclical ending known as the Big Crunch. This is the opposite of an accelerating expansion. If dark energy were to weaken and fade away, gravity could eventually win the cosmic tug-of-war. The expansion of the universe would slow, halt, and then reverse. All of creation would begin rushing back together. Galaxies would collide and merge in a fiery spectacle. The temperature of the entire cosmos would soar as everything is compressed into an incredibly hot, dense state, perhaps leading to a new Big Bang and a rebirth of the universe. So which of these fates awaits us? Current observations of distant supernova and the cosmic microwave background radiation, the afterglow of the Big Bang, point consistently toward the first option, the Big Freeze. The data suggests dark energy behaves very much like Einstein's cosmological constant, a steady, unrelenting force. This means the most likely future for our universe is not a dramatic collapse or a violent tear, but a long, slow, and lonely descent into cold and darkness. The cosmos appears destined for a quiet, eternal expansion, a final chapter written not with a bang, but with a whisper. Yet this quiet future rests on a critical assumption, one that scientists are now fiercely debating. Is the rate of the universe's expansion, the so-called Hubble constant, truly constant at all? The answer to this question has revealed a deep and troubling crack in the foundation of modern cosmology. This crisis is known as the Hubble Tension. On one side of the debate are scientists who study the very early universe. They use the cosmic microwave background, the faint afterglow of the Big Bang, as their ultimate time capsule. By meticulously analyzing the tiny variations in this ancient light, they can calculate what the expansion rate should be today, based on our standard model of cosmology. It is a bit like calculating how fast a tree should be growing today by studying the rings deep within its ancient trunk. Their answer is a very precise number. On the other side are astronomers who measure the expansion rate directly in our local modern universe. They use a cosmic ladder of distance markers, starting with pulsating stars called Cepheid variables, and culminating in those same Type 1, a supernova that discovered dark energy. They observe these objects in nearby galaxies to get a direct, real-time measurement of how fast the cosmos is expanding right now. This is like measuring the speed of the tree's growth by watching its outermost branches extend. Their answer is also a very precise number. The problem is, these two numbers do not match. They disagree significantly. The local measurement says the universe is expanding faster than the early universe measurement predicts it should be. This is not a small statistical fluke. The discrepancy is large enough that the chance of it being a simple error is less than 1 in a million. Something is very wrong. This Hubble tension suggests that our standard model of cosmology, which has been incredibly successful for decades, might be incomplete. Perhaps dark energy is not a simple cosmological constant, but is instead evolving, becoming stronger over time. Maybe there is a new, unknown type of subatomic particle that flooded the early cosmos, changing its evolution. Or perhaps our understanding of gravity needs a fundamental revision when applied to the entire universe. This single number, the Hubble constant, has become the front line in a battle for the soul of physics. Its persistent tension is a glaring clue that we are on the verge of a monumental discovery, one that could force us to rewrite the story of our universe from its very first moments. This fundamental disagreement about the universe's present expansion forces us to look back to its very first moments, to a concept so radical it redefined our origin story. The theory of cosmic inflation proposes that a fraction of a second after the Big Bang, the universe underwent a growth spurt of unimaginable speed. For a fleeting instant, space itself expanded faster than the speed of light, blowing up a subatomic speck of primordial stuff into a volume far larger than our entire observable cosmos. This idea elegantly solves several major puzzles. It explains why the universe appears so uniform in all directions, why it is geometrically flat, and most importantly, what seeded the formation of all future structures. According to inflation, the empty vacuum of space was not perfectly calm. It was fizzing with tiny, random quantum fluctuations, unpredictable little jumps in energy that happen on the smallest scales. During the inflationary period, these microscopic ripples were stretched to enormous cosmic proportions. They became the faint blueprint for all the future galaxies, stars, and planets. The rich tapestry of the cosmos, with its vast voids and brilliant clusters, originated from these subatomic seeds. Yet for all its success, inflation raises profound questions of its own. What was the engine that drove this incredible expansion? Physicists call it the inflaton field, a hypothetical energy field that permeated the infant universe. We do not know what this field is, or what kind of particle, the inflaton, is associated with it. It is a complete placeholder in our equations. Even more puzzling, what triggered inflation to start, and more mysteriously, what made it stop. The leading idea is that the inflaton field was in a high-energy state, like a ball perched at the top of a hill. This state gave space its repulsive gravity, causing the violent expansion. As the field slowly rolled down the hill of its potential, it eventually reached the bottom, and that energy was converted into the hot, dense soup of particles that filled the young universe. But why did this happen? Was it an inevitable outcome of physics, or just a random, lucky quantum event in a much larger multiverse? The mechanism that ended inflation, a process called reheating, remains one of the least understood chapters in cosmic history. We are left with a staggering thought. The entire universe we can see, with its hundreds of billions of galaxies, may be just a tiny bubble in an infinitely larger, eternally inflating cosmos, a single outcome of a process that created countless other universes with entirely different properties. This idea of a perfectly tuned cosmic expansion leads us directly to the geometry of the cosmos itself. What is the actual shape of the universe? We are not talking about the distribution of galaxies, but the fundamental geometry of space on its very largest scales. Is space flat like an infinite sheet of paper, or is it curved like the surface of a sphere or a saddle? The answer is written in the ancient light of the cosmic microwave background, and it reveals a universe that is, to an astonishing degree of precision, perfectly flat. This flatness means that the familiar rules of geometry we learned in school, where parallel lines never meet and the angles of a triangle always add up to 180 degrees, hold true across the vast cosmic expanse. This geometric simplicity, however, hides a profound and deeply puzzling secret. A flat universe is not just one possibility among many. It is a very specific, finely tuned condition that depends critically on the total density of all the energy and matter in the cosmos. Think of the universe's expansion as a delicate balancing act. If the density of the universe were too high, gravity would quickly overwhelm the expansion, causing space to curve back on itself into a closed, spherical shape. In this scenario, the universe would be finite, and if you traveled in a perfectly straight line, you would eventually loop back to your starting point, just as a ship sailing across the ocean can circumnavigate the Earth. If the density were too low, the universe would be open and hyperbolic, curving outward like a saddle. In this endless, negatively curved space, parallel lines would rapidly diverge. For the universe to be flat, the density must be exactly at the critical value, a perfect balance between these two extremes. The incredible puzzle is that our universe appears to be balanced exactly on this razor's edge. Measurements from the cosmic microwave background show that the actual density of the universe is incredibly close to this critical value. The margin of error is less than 0.5%. This presents a monumental fine-tuning problem. Why is the universe so perfectly flat? In the chaotic first moments after the Big Bang, for the flatness we see today to emerge, the initial conditions of the universe had to be fine-tuned to an unimaginable precision of 1 part in 10 to the power of 60. That is a 1 followed by 60 zeros. It is like balancing a pencil on its tip for billions of years, a feat so statistically unlikely that it screams for an explanation. The theory of cosmic inflation provides the most compelling answer. That violent, faster-than-light expansion in the universe's first instant would have stretched space so dramatically that it would have flattened its geometry, much like how blowing up a balloon makes a small, wrinkled patch appear increasingly smooth and flat. Inflation naturally drives the universe toward this critical density, solving the fine-tuning problem. Yet this solution raises another, even more dizzying possibility. If inflation made our observable universe flat, what is the shape of the entire cosmos beyond what we can see? Our local flat region could be just one small, level patch on a vast, convoluted landscape of space that may be curved in fantastically complex ways on scales far beyond our horizon. The simple, flat geometry we measure might be a local truth, but not the ultimate shape of reality. The perfect flatness of our universe is a clue that points toward an even grander cosmic architecture. This leads us to the sixth profound question. Are there other universes? The theory of eternal inflation suggests that the violent expansion that shaped our cosmos may never have completely stopped. Instead, it might be a perpetual engine of creation, where the fabric of spacetime is inflating at an incomprehensible rate for eternity. In this seething, expanding medium, random quantum fluctuations can cause tiny pockets of space to suddenly stop inflating. Each of these pockets undergoes its own version of the Big Bang, giving birth to a distinct universe, isolated from all the others. Picture a vast, boiling pot of water. The water itself represents the eternally inflating spacetime, expanding furiously. The bubbles that form and rise to the surface are individual universes like our own. This is the multiverse, a cosmic foam of countless bubble universes, each with its own unique properties. The laws of physics we consider fundamental and unchanging, the strength of gravity, the mass of an electron, even the number of spatial dimensions, might not be universal laws at all. They could be mere local bylaws, determined by the random way inflation ended in our particular bubble. In another universe, gravity might be so weak that no stars ever form. In another, The nuclear forces might be too strong, locking all matter into inert helium. The value of dark energy, that mysterious force driving our expansion, could also be a random accident. In most bubbles, the dark energy might be so powerful that it rips apart any nascent structures, or so weak that the universe collapses back on itself almost immediately. We just happen to live in a bubble where the value is strangely small and gentle, allowing for the billions of years of stable cosmic evolution needed for galaxies, stars, planets, and life to emerge. This idea finds a strange parallel in the mathematics of string theory, a candidate for a theory of everything. String theory allows for a staggering number of possible solutions, perhaps 10 to the power of 500 different configurations for the vacuum of space. Each configuration corresponds to a universe with different physical laws and constants. This vast landscape of possibilities seems to fit perfectly with the concept of a multiverse generated by eternal inflation. Our universe is not special. It is simply one that is compatible with our existence. Yet this radical idea is deeply controversial. If these other universes are permanently disconnected from our own, forever beyond the horizon of our observable cosmos, can we ever claim it is science? How could we possibly test for their existence? The multiverse may be the most natural explanation for the bizarre fine-tuning we observe, but it also challenges the very definition of what it means to seek an explanation for our reality. Are we one cosmic island in an infinite archipelago of worlds? Or is our universe all there is? The possibility of a multiverse pushes our origin story to its absolute limit, forcing us to confront the ultimate question. What caused the Big Bang itself? This inquiry immediately runs into a profound philosophical and physical wall. Our current understanding of time, space, and causality is built upon the framework of general relativity, and that framework breaks down completely at the moment of the Big Bang. The universe becomes an infinitely hot, infinitely dense point, a singularity where the laws of physics as we know them simply cease to apply. Asking what happened before the Big Bang might be like asking what is north of the North Pole. The concept of before may have no meaning if time itself was created in that initial event. Some theories, however, dare to venture beyond this singularity. One compelling idea is the cyclic universe model. Imagine a cosmos without a true beginning or end, an eternal rhythm of creation and destruction. In this scenario, our universe is just one phase in an endless cycle. It begins with a Big Bang, expands for trillions of years, and is eventually pulled back together by gravity in a big crunch. But instead of vanishing into nothingness, that incredibly dense, hot state bounces. It triggers a new Big Bang, birthing a fresh universe from the ashes of the old one. The cycle repeats forever, with each new universe inheriting a slight imprint from the one before it. There was no first cause, only an endless cosmic heartbeat. A different approach comes from the quest for a theory of quantum gravity, which seeks to unite general relativity with quantum mechanics. In this view, the Big Bang was not a true singularity, but a transition from a previous state of the cosmos. Perhaps our universe emerged from a cosmic seed, a tiny nugget of space-time from a parent universe. Or maybe it quantum tunneled into existence from literally nothing, a random fluctuation in a primordial void. In the quantum realm, particles pop in and out of existence all the time. Could the entire universe be the ultimate example of this phenomenon? Under the strange rules of quantum physics, the universe could have spontaneously appeared, a fluctuation that simply refused to disappear. This leads to the most mind-bending possibility of all. a beginningless universe. Perhaps time is an emergent property, not a fundamental feature of reality. Just as the concept of temperature emerges from the frantic motion of countless molecules, but has no meaning for a single atom, time might emerge from a more basic, timeless quantum state. Our linear perception of past, present, and future, with a definitive starting gun, could be an illusion. The Big Bang would then not be the beginning of time, but the moment when the universe became classical and recognizable, emerging from a timeless quantum fog. We are left staring into an abyss of questions, where our most fundamental concepts of cause and effect dissolve. The search for a first cause may be a fool's errand, pointing toward a reality far stranger and more magnificent than we ever imagined. This connection between the quantum and the cosmic is one of the most astonishing ideas in all of science. The entire grand architecture of the universe, every galaxy and every void, can be traced back to the ghostly, unpredictable fizz of the quantum world. In the first fleeting moments, the vacuum of space was not empty and calm. It was a seething sea of potential, where pairs of virtual particles and energy fluctuations spontaneously popped in and out of existence, a quantum foam of reality itself. These fluctuations were unimaginably tiny, operating on scales billions of times smaller than a single atom. They were the faintest possible whispers in the fabric of spacetime. Then inflation happened. That period of faster-than-light expansion acted like a cosmic amplifier, stretching these subatomic ripples to proportions beyond comprehension. A quantum jitter that was once smaller than a proton was, in less than a blink of an eye, inflated to a size of many light years across. These stretched fluctuations were not in matter itself, but in the very density of the universe. Some regions became ever so slightly denser than others. In the aftermath of inflation, gravity got to work. Those slightly denser patches had a tiny bit more gravitational pull. Over hundreds of millions of years, they acted as seeds, pulling and surrounding dark matter and gas. The slightly denser regions grew denser still, eventually collapsing under their own gravity to form the first stars, galaxies, and the vast filamentary cosmic web we observe today. The entire rich structure of the cosmos was imprinted by these quantum seeds. We can see the direct evidence for this in the cosmic microwave background. The tiny temperature variations, the hot and cold spots in that ancient light, are a frozen baby picture of those very density fluctuations. They map the initial conditions that would one day give rise to everything we know. Yet this incredible story contains a deep and unresolved mystery. How does a quantum fluctuation, which is inherently probabilistic and fuzzy, become a fixed, classical seed for a galaxy? In the quantum realm, a particle exists in a haze of probabilities until it is observed or measured, a process known as decoherence that forces it to pick a definite state. But in the early universe, there was no external observer. What was the measurement that collapsed these quantum waves into the concrete density variations that gravity could then act upon? Some physicists believe the rapid expansion of inflation itself performed this cosmic measurement, stretching the quantum fluctuations so rapidly that they lost their quantum coherence and became frozen into the classical landscape of the cosmos. Others suggest that the gravitational interaction between these fluctuations was enough to force them into a definite state. The transition from the probabilistic quantum world to the definite classical universe remains one of the most profound frontiers in physics. It suggests that the largest structures we see when we look at the night sky are, at their heart, magnified quantum events, a permanent record of the universe's first and most fundamental uncertainty. This invisible cosmic scaffolding is the other great mystery shaping our universe. We call it dark matter, and its gravitational influence is the primary architect of the cosmos we observe today. Think of the universe's expansion as the canvas stretching, but dark matter provides the gravitational wells where paint can gather to form the brilliant structures of galaxies and clusters. Without dark matter's immense gravitational pull, the initial expansion after the Big Bang would have been too rapid, scattering the primordial gas so widely that galaxies and stars could never have coalesced. Its presence is felt everywhere, yet it remains utterly elusive, a ghostly substance that neither emits nor reflects light. We only know it's there because of the way its gravity tugs on the things we can see. Stars on the outer rims of galaxies whirl around at speeds that should fling them into the intergalactic void, yet they remain securely bound. Entire clusters of galaxies move in ways that would be impossible if the only gravity present came from the glowing stars and gas we detect. Something unseen, weighing far more than all visible matter, is holding the cosmic structures together. This dark matter forms a vast, invisible skeleton across the universe, and the luminous galaxies are merely the glittering ornaments hanging upon it. The nature of this mysterious substance is one of physics' most pressing quests. The leading candidate is a hypothetical particle known as a WIMP, a weakly interacting massive particle. These particles would be heavy, stable, and interact with ordinary matter only through gravity and the weak nuclear force, making them incredibly difficult to catch. For decades, scientists have built exquisitely sensitive detectors deep underground, shielded from cosmic rays, hoping to sense the minuscule bump of a WIMP colliding with an atomic nucleus. So far, the detectors have remained silent. Other experiments search for indirect evidence, scanning the skies for unusual gamma rays or other radiation that could be produced if dark matter particles annihilate each other in the dense cores of galaxies. If dark matter is not a WIMP, it could be something even stranger like actions, which are incredibly light particles, or even primordial black holes formed in the universe's first second. The frustrating truth is that after decades of searching, we still do not know what the majority of matter in the universe is made of. This ignorance directly impacts our understanding of cosmic expansion. The amount and behavior of dark matter determine how cosmic structures form and evolve, which in turn influences how we measure the expansion history of the universe. If dark matter has properties we haven't yet imagined, it could be a hidden key to resolving the Hubble Tension, that troubling discrepancy in the expansion rate. The hunt for this ghostly substance is not just a side quest. It is central to the grand narrative of our cosmos, from its first structures to its ultimate fate. The ghostly nature of dark matter hints at a deeper cosmic order. But what happens when that order is challenged by the most destructive objects in existence? This brings us to the 10th great mystery. Is the universe losing information in black holes? A black hole is a region of space where gravity is so intense that nothing, not even light, can escape its pull. According to Einstein's general relativity, if you were to throw an encyclopedia, a piano, and a spaceship into a black hole, all that intricate information about their composition and structure would be permanently lost, crushed into a single point of infinite density at the center, the singularity. The black hole itself would only be characterized by its mass, its spin, and its electric charge. This presented a catastrophic problem for physics, because quantum mechanics insists that information can never be truly destroyed. The universe, at its heart, is predictable. If you know the complete state of a system, you should, in principle, be able to run the clock backwards and forwards to see its past and future. The total amount of quantum information must be conserved. If black holes destroy information, then the very foundation of quantum theory is wrong. The conflict between these two pillars of physics became known as the black hole information paradox. A potential resolution came from Stephen Hawking. He discovered that black holes are not entirely black. Due to quantum effects at their event horizons, they slowly emit a faint glow of radiation, causing them to lose mass and eventually evaporate completely over astronomical timescales. The problem was that this Hawking radiation was predicted to be purely random, carrying no information about what fell in. So when the black hole finally vanishes, all the information it ever swallowed would be lost forever. This paradox suggests that our understanding of reality breaks down in these extreme gravitational environments. How does this connect to the universe's expansion? The ultimate fate of our cosmos, that long, cold Big Freeze, presents a similar information crisis on a universal scale. As the universe expands and accelerates, distant galaxies will be pushed beyond our cosmic horizon, their light forever lost to us. The universe becomes a collection of isolated islands, each unable to communicate with the others. In a very, very distant future, the last stars will die, and black holes will dominate the cosmos before they too evaporate via Hawking radiation. If that radiation is truly random and information-losing, then the final state of the universe would be a thin, cold, and featureless haze of particles, a state with no memory of its glorious, structured past. All the information about every galaxy, every star, every planet, and every life form would be erased from reality. The universe would have no history. Most physicists now believe that information is not lost in black holes. The leading idea is that the information is not destroyed, but is somehow encoded on the surface of the black hole's event horizon, a concept known as the holographic principle. It is then scrambled and slowly radiated back out in the Hawking radiation, albeit in an incredibly complex and hidden form. The black hole acts like the ultimate cryptographic device. If this is true, then perhaps information can also be preserved through the universe's entire life cycle, even as it expands into darkness. Yet this remains an unproven hypothesis. The fate of information is tied to the fate of the cosmos itself. Does the universe remember what it was, or does its final expansion into cold nothingness represent the ultimate act of cosmic forgetting? Every single structure in our universe, from the grandest galaxy to the smallest living cell, exists only because of a profound and unexplained cosmic imbalance. The laws of physics, as we currently understand them, suggest that the Big Bang should have created equal amounts of matter and antimatter. For every proton born, an antiproton should have appeared. For every electron, a positron. Matter and antimatter are perfect mirror images, and when they meet, they annihilate each other in a flash of pure energy. If the cosmos had been perfectly symmetrical, every particle of matter would have found its antimatter twin, and the entire universe would have dissolved into a uniform bath of radiation, leaving behind no atoms, no stars, and certainly no life. Yet here we are in a universe overwhelmingly dominated by matter. So what happened to all the antimatter? This is the puzzle of baryon asymmetry, one of the most fundamental enigmas in all of science. Something in the early universe must have tipped the scales, violating the sacred symmetry between matter and antimatter. Physicists call this process baryogenesis. For it to occur, 3 conditions had to be met in the hot, dense plasma of the infant cosmos. there had to be interactions that did not treat matter and antimatter equally, a violation known as CP violation. The universe had to be out of thermal equilibrium, meaning it couldn't be in a stable, uniform state. And these processes had to involve interactions that do not conserve the total number of particles, like those predicted by grand unified theories. The weak nuclear force, which governs radioactive decay, does exhibit a tiny amount of CP violation, but it is far too small to account for the overwhelming matter dominance we see today. The imbalance it produces is like saving just one single grain of sand from a beach that was completely annihilated. The rest of the antimatter is simply gone. This suggests that a much more powerful mechanism must have been at work in the first fractions of a second after the Big Bang, possibly during the epoch of cosmic inflation or immediately after. The rapid expansion of the universe itself may have been the key, creating the necessary conditions out of equilibrium and amplifying a small, initial bias into the cosmic reality we inhabit. The search for the source of this asymmetry is a hunt for new physics. It might be found in the behavior of ghostly neutrinos. Could these elusive particles be their own antiparticles? And could their interactions have preferentially created matter? Or does the answer lie in the realm of speculative theories, like supersymmetry, which predicts a whole new family of particles whose decays could have favored matter over antimatter? Experiments at particle colliders like the Large Hadron Collider are desperately searching for any sign of these new phenomena or any stronger violation of the matter-antimatter symmetry. The existence of our material world is the ultimate evidence that our current model of particle physics is incomplete. We are literally made from the 1 part in a billion that survived the universe's first and most violent annihilation. The fact that we are here to ponder this question is proof that the cosmos is not perfectly symmetrical, and that its initial expansion somehow wrote a profound bias for existence into the very fabric of reality. This profound bias for matter hints at a deep crack in our cosmic assumptions, a crack that becomes terrifyingly clear when we stare into the afterglow of creation itself. The cosmic microwave background should be a nearly perfect, uniform tapestry, a random splatter of hot and cold spots reflecting the quantum seeds of the early universe. Yet when scientists map this ancient light with incredible precision, they find bizarre, large-scale patterns that defy simple explanation. One of the most unsettling is a strange alignment astronomers have nicknamed the axis of evil. This is not a malevolent force, but a statistical ghost in the machine. The hot and cold spots in the cosmic microwave background are not oriented randomly across the sky as the standard model predicts. Instead, they appear to be aligned along a particular plane, a preferred direction in the cosmos that seems to point toward the constellations of Leo and Virgo. This alignment, or quadrupole moment, suggests the universe might have a handedness, a spin, or a fundamental lopsidedness that should not exist. The cosmological principle, the bedrock of modern cosmology, states that the universe is homogeneous and isotropic. On the largest scales, it should look the same in every direction, with no special places and no preferred axis. The axis of evil directly challenges this foundational idea. It is as if you walked into a room that was supposed to be perfectly round and found that all the furniture was mysteriously lined up facing one specific wall. What could cause such a coordinated pattern on a cosmic scale? Some theorists suggest it might be a remnant of something that existed before the Big Bang, a pre-existing structure or anisotropy that imprinted itself onto our newborn cosmos. Perhaps our universe is not a lone, isolated bubble, but is brushing up against another universe in the multiverse. Its gravitational influence subtly tugging at the fabric of our reality and creating this strange alignment. Others propose it could be evidence of an exotic form of dark energy or a complex field that twisted space-time in the first instant. There is another chilling anomaly, a vast, inexplicably cold spot in the southern sky, a region so large and so much colder than its surroundings that it is incredibly difficult to explain with standard physics. It could be a cosmic texture, a defect in the fabric of space-time left over from a phase transition in the early universe, like a crack in a frozen lake. Or it could be a sign of a colossal void, a truly empty region of space so vast that the light crossing it loses more energy than our models allow. These anomalies are more than just statistical curiosities. They are direct challenges to the inflationary paradigm, which predicts a universe that is, on average, smooth and featureless. If these patterns are real and not just a fluke of our particular viewpoint, they force us to reconsider the entire story of cosmic expansion. Was inflation not the whole story? Does the universe remember a time before time began? The axis of evil and its companion mysteries remain unsolved, a haunting whisper from the edge of the observable cosmos that our map of reality is still missing fundamental pieces. These cosmic anomalies whisper that our physical laws might not be as fixed as we believe. What if the very rules of the game have been changing all along? We take for granted that fundamental constants, like the speed of light or the strength of gravity, are immutable pillars of reality. But what if they are not? The idea that these numbers might be slowly drifting as the universe expands is one of the most radical propositions in modern physics. Imagine the fine structure constant, a number that governs the strength of the electromagnetic force. This force holds atoms together and dictates how light interacts with matter. If this constant were just a few percent different, the chemical bonds that form molecules would fail. Stars would be unable to burn, and complex matter would be impossible. Our existence hinges on its precise value. For decades, scientists have tested this constancy by studying the light from incredibly distant quasars, the brilliant cores of ancient galaxies. This light has traveled for billions of years across the cosmos, and on its journey, it passes through vast clouds of interstellar gas. These clouds imprint a unique fingerprint on the light absorption lines that act as a cosmic barcode, encoding the properties of atoms in the early universe. Some teams have analyzed this ancient barcode and reported a tantalizing, controversial result. The patterns suggest that the fine structure constant might have been slightly different billions of years ago. The electromagnetic force could have been a tiny fraction weaker in the distant past. This is not a settled fact, and other observations have found no such change. But if it is true, the implications are staggering. It would mean that the laws of physics are not written in stone, but are more like a language that evolves over time. The cosmos would be a much more dynamic and fluid place than we ever imagined. How would this affect the universe's expansion? A changing constant could directly mimic or even explain the effects of dark energy. If the strength of gravity itself has been slowly weakening over cosmic history, that would cause the expansion of the universe to accelerate, exactly as we observed. We might not need a mysterious dark energy at all, just a subtle, fundamental shift in the force that binds the cosmos together. This idea connects to theories that attempt to unify all forces, like string theory, which often predict the existence of new, dynamic fields that could slowly alter what we think of as constants. The stability of our reality might be an illusion, a temporary phase in a much longer cosmic story where the rules themselves are written in fading ink. This staggering fine-tuning of our material existence points toward a vacuum that is anything but empty. The space between stars and galaxies is not a true void. According to quantum field theory, it is a seething, bubbling sea of activity. Virtual particle pairs constantly flash into and out of existence, borrowing energy from the vacuum for fleeting moments before annihilating each other. This endless dance gives the vacuum itself a fundamental energy, a baseline hum of reality known as vacuum energy. This is where we run headlong into the most embarrassing problem in all of physics. When physicists use their most successful theories to calculate how much energy this quantum vacuum should contain, they get a number. And it is a number of such monumental wrongness that it represents the largest discrepancy between theory and observation ever recorded. The calculated value is 10 to the power of 120 times larger than the energy density we actually observe for dark energy. That is a 1 followed by 120 zeros. To grasp the sheer scale of this error, imagine predicting that a single grain of sand should weigh more than the entire observable universe. The prediction is not just a little off. It is catastrophically, impossibly incorrect. This is the cosmological constant problem, and it screams that we are missing something profound about the nature of reality. Why is the observed vacuum energy so incredibly close to zero, but not quite zero? If it were exactly zero, we might find an elegant symmetry in nature that forces it to be nothing. But it has a small, positive value, which is what drives the accelerated expansion of the universe. This tiny but crucial number is the reason galaxies are flying apart. So why does our best theory predict a universe that should have torn itself to shreds in its first instant? One possibility is that we are fundamentally misunderstanding the vacuum. Perhaps the contributions from all these quantum fields somehow cancel each other out with unimaginable precision, leaving only this faint residual energy we call dark energy. But such a cancellation would require a level of fine-tuning that seems just as miraculous as the problem it tries to solve. Another, more radical idea is that the vacuum energy does not gravitate in the way we think it does. Maybe the relentless creation and destruction of virtual particles simply does not produce a gravitational effect that couples to the large-scale expansion of the universe. Our concept of how quantum mechanics and gravity intertwine is still in its infancy, and this colossal failure of prediction is the clearest possible sign that our models are broken. The vacuum of space holds the key to the fate of the cosmos, and right now, our best theories cannot explain why it is so quietly, delicately calm. This profound enigma of the vacuum forces us to question an even more fundamental aspect of our reality. Is time itself an illusion? Our daily lives are governed by its relentless, one-way flow from past to present to future. Yet physics paints a strangely different picture. According to Einstein's theory of relativity, time is not a universal river flowing at the same rate for everyone. It is a dimension, woven together with the 3 dimensions of space into a single, 4-dimensional fabric called spacetime. In this view, the entire history of the universe, from the Big Bang to the distant future, might be fixed and eternal, a static block where the past, present, and future all exist simultaneously. This is the block universe theory. Your birth, your life, and the ultimate fate of the cosmos are all just different coordinates in this vast, unchanging structure. There is no special now, no flowing river, just a cosmic landscape where every event has its permanent place. This feels deeply wrong to our intuition. We experience time as a progression, a sequence of moments. So where does this arrow of time come from? The most compelling clue lies in a concept from thermodynamics called entropy, which is a measure of disorder. The universe began in a state of incredibly low entropy, a highly ordered and dense configuration at the moment of the Big Bang. Since then, entropy has been steadily increasing, moving from order to disorder. We see this everywhere, from a shattered glass that never reassembles itself to the way heat always flows from a hot object to a cold one. This relentless increase in disorder gives us a powerful direction for time. The arrow of time and the expansion of the universe are deeply intertwined. As the cosmos expands, it creates more room for particles to spread out and for energy to become more diffuse, which directly increases the total entropy of the universe. The expansion itself may be the engine driving the arrow of time. Without this cosmic unfolding, time might have no preferred direction. Could time be an emergent property rather than a fundamental one? Just as the concept of wetness emerges from the collective behavior of countless water molecules, but has no meaning for a single molecule, our perception of time's flow might emerge from the complex interactions and increasing entropy within the universe. In this view, time is not a primary ingredient of reality, but a secondary consequence of the universe's journey from a low entropy beginning to a high entropy end. If the universe were to eventually stop expanding and begin to contract in a big crunch, would the arrow of time reverse? Would entropy begin to decrease, causing broken glasses to reassemble and people to grow younger? Most physicists think not. The low entropy beginning seems to be a unique, one-time boundary condition that sets the direction for all time, regardless of the expansion's fate. The expansion provides the arena for entropy to increase, but the initial low entropy state is the true source of the arrow. So is time real, or is it the ultimate cosmic mirage? The flow we feel may be a profound illusion, a story our brains tell us as we move through the fixed landscape of the block universe, conscious of only a single slice of the eternal now at any given moment. The universe expands, entropy increases, and we, caught in the current, mistake this journey for the fundamental nature of time itself. Out of the darkness that followed the Big Bang, the first stars were born. These were not like the stars we see today. They were colossal behemoths, hundreds of times more massive than our sun, and they blazed with a ferocious, short-lived intensity, flooding the young cosmos with its first true light. This transformative era is known as the Epoch of Reionization, and it marks one of the most profound transitions in cosmic history. For hundreds of millions of years after the Big Bang, the universe was a featureless, opaque fog of neutral hydrogen gas. Light could not travel freely, as these atoms would simply absorb any photons trying to pass through. The cosmos was adrift in a formless gloom. Then, the first stars and galaxies ignited. Their intense ultraviolet radiation began to tear the electrons away from the protons in the surrounding hydrogen gas, a process called ionization. One by one, then in a rapidly expanding wave, these cosmic bubbles of ionized plasma began to form and overlap, slowly burning away the primordial fog. Over several 100 million years, the entire universe was reionized, transforming from an opaque sea into the crystal-clear, transparent expanse we observe today. But how did this happen so quickly? How did these first structures assemble in an expanding universe that was still relentlessly stretching everything apart? The answer lies in the invisible hand of dark matter. While ordinary matter was buffeted by the pressure of radiation, dark matter, unaffected by light, was already collapsing under its own gravity. It formed a vast, invisible scaffolding of halos, gravitational wells where ordinary matter could finally settle. Think of dark matter as creating deep valleys in the fabric of expanding space. The hydrogen gas, flowing like water, collected in these valleys, pooling into densities high enough to trigger the collapse of the first stars and proto-galaxies. This was not a gentle process. Supercomputer simulations of this era show a violent and chaotic cosmos. Dark matter halos merged and grew, cannibalizing each other in a frantic dance of gravitational capture. Within these halos, the first stars are thought to have formed not in calm nurseries, but in frantic, turbulent bursts, living fast and dying young in spectacular supernovae that seeded the universe with the first heavy elements. Yet for all the power of our simulations, this epoch remains shrouded in mystery. We have never directly observed these first-generation stars, known as population 3 stars. What were their exact properties? Did they form in isolation or in dense clusters? How exactly did their radiation punch through the fog and orchestrate the large-scale reionization of the cosmos? Our current telescopes can only see the very end of this process, the last vestiges of the fading fog, the true dawn of light, the moment the very first stars switched on in the infinite darkness, is still hidden from our view, a silent revolution at the edge of time. The darkness beyond the edge of our vision holds one of the most tantalizing questions of all. What is beyond the cosmic horizon? We live inside a bubble of observable space. A sphere defined by the distance light has had time to travel in the 13.8 billion years since the Big Bang. This horizon is not a physical wall, but a limit in time. We cannot see what lies beyond it, not because it is too dark, but because the light from those regions has not reached us yet. And due to the universe's accelerating expansion, it never will. Those distant realms are forever receding from our view, lost to the stretching fabric of space. So what lies in that eternal darkness? The simplest answer is simply more of the same. An endless continuation of galaxies, stars, and cosmic voids, stretching into an infinite expanse. Our entire observable universe, with its hundreds of billions of galaxies, would then be just a single grain of sand on an infinite beach. Yet the strange geometry of our cosmos suggests another possibility. Remember the universe's perfect flatness. An infinitely large, flat universe is one of the few geometries that fits our data. If space truly is infinite, then beyond our horizon, the possibilities become staggering. Every possible configuration of matter, every variation of physical law that can exist, must exist somewhere. There would be regions where the constants of physics are slightly different, where dark energy is stronger or weaker, and even regions identical to our own, where copies of you and me are pondering this very same question. This is not necessarily the multiverse of inflation, but a consequence of infinite space. But infinity is not the only option. Perhaps the entire cosmos is finite, but curved in upon itself in a way we cannot perceive. Like an ant on the surface of a gigantic balloon, we would never encounter an edge, but the total amount of space would be limited. The structure of what lies beyond our horizon could then be fantastically complex, a convoluted geometry of space that loops back on itself or connects to other domains in a cosmic foam. The driving force behind this eternal concealment is the same dark energy that dictates our fate. The accelerating expansion is constantly shrinking our observable universe, pushing more and more galaxies beyond the light horizon. We are living in a cosmic oasis that is slowly evaporating, its borders forever closing in. Each day, the realm of the knowable grows smaller, and the great unknown beyond becomes vaster and more permanent. We are forever isolated, prisoners within our own expanding bubble of spacetime, destined to only ever know a tiny fraction of the whole. So is the greater universe an infinite tapestry of familiar forms, or a finite, intricately folded knot of space? Is it a chaotic landscape of bubble universes, each with its own unique laws, as eternal inflation suggests? We may never have a definitive answer. The ultimate nature of reality may be fundamentally, tragically unknowable, hidden from us by the very expansion that defines our cosmos. The very fabric of our reality might be an illusion, a mere slice of a far richer cosmos. We perceive 3 dimensions of space, but what if there are more, hidden from our senses, yet subtly shaping the universe we see? This is not science fiction, but a serious prediction of string theory, our most promising candidate for a theory of everything. To unify gravity with quantum mechanics, string theory requires extra spatial dimensions, perhaps 6 or 7 of them, all curled up into a space so fantastically small that they are utterly invisible to us. These dimensions could be as minute as the so-called Planck length, a billionth of a trillionth of the size of an atomic nucleus. But how could such tiny, hidden realms possibly affect the grand expansion of the cosmos? The influence might be profound. Imagine our 3-dimensional universe as a vast, infinite sheet of paper, a membrane floating within a higher dimensional bulk. This is the brain world scenario. All the particles and forces we know, except for one, might be trapped on this membrane, unable to leave its surface. The one exception is gravity. Gravity, in this picture, is the curvature of spacetime itself, and it could be free to leak into the extra dimensions. This leakage would explain why gravity is so unimaginably weaker than the other fundamental forces. Its strength is simply diluted as it spreads out into the higher dimensional space. If this is true, then the force of gravity in the early universe would have been stronger, as the extra dimensions were more compact. This change in the strength of gravity over cosmic time could directly influence the rate of the universe's expansion, potentially offering a solution to the Hubble tension without the need for evolving dark energy. The expansion we measure could be a shadow, a 3-dimensional projection of a more complex dynamical process occurring in a higher dimensional reality. So how could we ever detect these hidden dimensions? One possibility lies in the violent collisions of cosmic objects. When black holes or neutron stars merge, they send ripples through spacetime called gravitational waves. If gravity can indeed leak into extra dimensions, then some of the energy from these cataclysmic events might vanish into the higher dimensional bulk. Our detectors like LIGO and Virgo would measure a gravitational wave signal that is subtly weaker than predicted, a missing energy signature that points to an unseen escape route. Another tantalizing prospect involves particle accelerators like the Large Hadron Collider. If we can muster enough energy, we might be able to probe these tiny, curled-up dimensions directly. The collisions could, in theory, produce particles that briefly travel into an extra dimension before snapping back into our own, appearing to us as a sudden, inexplicable disappearance of energy and momentum. Or, even more dramatically, we could create microscopic black holes, objects whose existence and properties would be a smoking gun for the higher dimensional nature of reality. The hunt for extra dimensions is a hunt for the true architecture of existence. Their discovery would not only revolutionize physics, but would force us to reinterpret the entire history of cosmic expansion. revealing that the story of our universe is written in more than just 3 dimensions. This final frontier of hidden dimensions brings us to the very heart of the conflict. Our two most successful theories of reality, general relativity and quantum mechanics, are at war over the nature of gravity itself. General relativity paints gravity as the elegant curvature of spacetime, a smooth geometric landscape that explains the cosmos from orbiting planets to the universe's expansion. Quantum mechanics describes a frantic, probabilistic world where particles pop in and out of existence and forces are mediated by tiny packets of energy. These two frameworks are fundamentally incompatible. When we try to apply quantum rules to the gravitational field, the mathematics explodes into infinities, giving nonsensical answers. This battle is fought at the extremes, in the first moment of the Big Bang and at the center of black holes, where the immense gravity of a singularity meets the fuzzy uncertainty of the quantum world. To truly understand the origin and fate of our expanding universe, we need a theory of quantum gravity, a single set of rules that can describe the fabric of reality at its absolute smallest scale. One bold approach is loop quantum gravity. This theory suggests that space itself is not a smooth, continuous backdrop, but is woven from a fabric of tiny, finite loops. Picture the universe as a tapestry made of individual, interwoven threads. These threads of space form a network where the smallest possible area is a single stitch, and the smallest possible volume is a single knot. This granular structure prevents the formation of a true singularity of infinite density. In this view, the Big Bang was not the beginning of everything, but a great bounce. The universe we inhabit could have been born from the collapse of a previous cosmic phase, compressed to a tremendously high density until the quantum nature of spacetime itself caused it to rebound, launching the expansion we see today. Our entire cosmic history might be just one cycle in an endless series of bangs and crunches. The other great contender is string theory, which we just encountered. It proposes that the fundamental constituents of reality are not point-like particles, but incredibly tiny, vibrating strings. The different vibrational patterns of these strings give rise to all the particles and forces we observe. Crucially, one of these vibrational patterns always produces the particle that carries the gravitational force, the graviton seamlessly weaving gravity into the quantum tapestry. String theory's requirement for extra dimensions is its most radical and controversial feature, suggesting that the true nature of gravity is hidden from our three-dimensional perception. How would a theory of quantum gravity reshape our story of cosmic expansion? It could completely rewrite the first chapter. It might replace the mysterious singularity of the Big Bang with a concrete transition from a prior state, revealing what, if anything, came before. It could explain the initial trigger for inflation or show that dark energy is a manifestation of the quantum vacuum's true underlying structure. The ultimate goal is to peer into that first moment of time and finally answer the question of how our vast, expanding universe could have emerged from a realm where the very concepts of before and after lose all meaning. The search for quantum gravity is the quest for the final rulebook of the cosmos, a set of laws that can narrate the entire story, from the first quantum flicker to the last fading galaxy. Our expanding universe contains hundreds of billions of galaxies, each with billions of stars, and countless planets orbiting in their habitable zones. The sheer numbers suggest that life, even intelligent life, should be commonplace. Yet when we gaze into the cosmic ocean, we are met with an eerie, profound silence. This contradiction is the Fermi paradox. a cosmic riddle that asks a simple, haunting question. Where is everybody? The universe has had over 13 billion years for civilizations to arise, to flourish, and to spread across the galaxy. The silence we observe is deeply unsettling. One possible explanation is the existence of a great filter, a barrier so formidable that almost no life can pass beyond it to achieve interstellar travel or communication. This filter could lie in our past. Perhaps the spontaneous origin of life from non-living chemistry is an event of such staggering improbability that we are the only ones to have won that cosmic lottery. Or maybe the filter is the evolution of complex multicellular life, a jump that required a series of perfect biological accidents. The more terrifying possibility is that the great filter awaits us in our future. It could be that almost every advanced civilization eventually discovers a technology that leads to its own destruction, whether through nuclear war, engineered pandemics, or a runaway artificial intelligence. The silence of the cosmos would then be a graveyard of worlds that failed to survive their own technological adolescence. Another cosmological answer considers the vast stretches of time and space. Civilizations might bloom and wither like fireflies in the night, their lifetimes and territories so brief and small compared to the galaxy's immense age and scale. We could be isolated not just in space, but in time, our existence a fleeting spark in a long, dark cosmic history. Or perhaps they are out there, but the methods of their communication are so advanced, so fundamentally different from our radio telescopes, that we simply do not recognize their signals. They might have transcended biological forms entirely, living as post-biological intelligences in simulated realities, with no interest in reaching out to a young species like ours. The relentless expansion of the universe itself adds another layer of isolation. As galaxies fly apart, the window for cosmic conversation may be closing. Civilizations in different galaxy clusters are being swept beyond each other's cosmic horizons by dark energy, forever lost to one another before they ever have a chance to make contact. The great silence is a puzzle written in the stars, a mystery that forces us to confront our own place in a cosmos that seems perfectly designed for life, yet remains utterly, mysteriously empty. That violent inflationary expansion had to end, and when it did, it unleashed the fire of creation. The universe was still cold and empty after inflation, a vast, stretched-out void filled only with the energy of the inflatoned field. Then, in a process known as reheating, everything changed. This was the moment the universe truly became hot. The instant the energy that powered inflation was transformed into the seething, dense soup of particles that would become the Big Bang. Think of it like winding up a gigantic cosmic spring during inflation. Reheating was the moment that spring was released. It stored energy, flooding the cosmos with heat and matter. The inflatoned field, which had been perched in its high energy state, began to oscillate wildly around the bottom of its energy hill. These violent oscillations acted like a cosmic bell, ringing through the fabric of space and creating ripples that decayed into a torrent of fundamental particles, radiation, and other fields. It was the ultimate act of alchemy, turning the pure energy of empty space into the quarks, electrons, and photons that would build every star and planet. Yet the precise mechanism of this transformation remains one of the least understood chapters in our cosmic history. We do not know exactly how the inflatoned field coupled to, or interacted with, the other particles. Was it a slow, resonant transfer of energy, or a sudden, explosive instability that ripped particles into existence? The details of this handoff are critical, because they determine the initial conditions for the entire hot Big Bang. The efficiency and temperature of reheating set the stage for everything that followed, from the formation of the first atomic nuclei to the eventual birth of galaxies. If reheating had been even slightly less efficient, the universe would have been too cold and dilute for structures to ever form. If it had been too violent, it might have created a chaotic mess of exotic particles and defects. We exist in a universe that seems to have been reheated just right, but we have no idea how the controls were set. Unraveling the mystery of reheating means understanding the very first moments of our material existence, the fleeting instant when a cold, empty universe was set ablaze. This radical idea that information is not lost but encoded on a surface brings us to one of the most mind-bending concepts in all of physics. Is our universe a hologram? The holographic principle proposes a reality so strange it seems borrowed from science fiction. It suggests that all the information describing everything within a three-dimensional volume of space, every star, every planet, every person, is actually encoded on a two-dimensional surface that surrounds it, like a cosmic film projector. The three-dimensional world we experience, with its depth and solidity, would then be a magnificent illusion, a holographic projection from that underlying boundary. This is not mere speculation. The mathematics of black holes strongly hints that this might be true. The entropy, or the information content, of a black hole is not proportional to its volume, as you might expect. Instead, it is precisely proportional to the surface area of its event horizon. The maximum amount of information that can be stored in any region of space appears to be determined by the size of its surrounding surface, not by the volume inside. This is a profound clue that the fundamental degrees of freedom of our universe might live on a lower dimensional surface, and our reality is a projection. How could this possibly relate to the expansion of the cosmos? If the holographic principle is correct, then the evolution of the entire universe, its expansion and acceleration, might be governed by processes happening on a distant theoretical boundary. Cosmologists have explored models where our expanding universe is dual to, or described by, a quantum field theory without gravity living on its boundary. In this view, the mysterious effects of dark energy and the accelerating expansion we measure could be a shadow, a consequence of complex quantum interactions playing out on the edge of reality. The force we call gravity might not be a fundamental force at all, but an emergent phenomenon, something that arises from the collective, entangled information stored on that vast cosmic hard drive. Think of a whirlpool in a river. The whirlpool is not a fundamental entity. It emerges from the complex, collective motion of countless water molecules. In the same way, gravity and the very fabric of spacetime might emerge from the intricate patterns of quantum information encoded on the universe's boundary. This would mean that the expansion of space is not the stretching of a primary substance, but the changing projection of a deeper, more fundamental quantum reality. The holographic universe challenges everything we assume about existence. The solidity of the world around you, the vast distances between galaxies, the relentless push of dark energy, all of it might be a grand and convincing illusion. We are left wondering if we are living inside the most complex simulation imaginable, a cosmic hologram whose source code is written in a language of quantum information on the ultimate edge of everything we can ever know. These cosmic magnetic fields are invisible threads woven through the fabric of the cosmos. They stretch between galaxies and swirl within colossal galaxy clusters, a pervasive force that should not, according to our standard models, be there? Their origin is a deep and enduring mystery, one that must be explained within the relentless context of an expanding universe. How did these immense magnetic fields, spanning tens of thousands of light years, come to exist? The most straightforward idea is that they grew from tiny seeds. In the hot, seething plasma of the early universe, small electrical currents could have been generated by various processes. Perhaps they were born from the turbulent motions of that primordial soup during the epoch of structure formation. Maybe they were even imprinted by the violent events of inflation itself, a quantum fluctuation stretched to cosmic proportions. These would have been incredibly weak fields, billions of times fainter than the magnetic field of the Earth. The mystery is not their initial spark, but their incredible amplification. A process must have taken these faint seeds and turned them into the powerful fields we observe today. The leading theory involves a cosmic dynamo. Imagine a simple magnetic field line running through a spinning disk of a young galaxy. As the galaxy rotates, it drags this field line along, twisting and stretching it. The turbulent motions of the ionized gas within the galaxy further tangle and wind these lines, effectively transferring the rotational energy of the galaxy into magnetic energy. Over hundreds of millions of years, this dynamo effect could have amplified a vanishingly small seed into the structured field that now guides cosmic rays and influences star formation. But the timeline is desperately tight. The expansion of the universe was constantly working against this process, diluting the density of the galactic gas and making it harder for the dynamo to operate efficiently. We see fully formed magnetic fields in galaxies that are very young, suggesting this amplification had to happen with surprising speed. This forces us to consider whether the initial seeds were stronger than we think, or if there is a crucial piece of physics missing from our models of galactic evolution. The puzzle deepens when we look at the voids between galaxies. Astonishingly, even these vast, nearly empty regions appear to be magnetized. How could a galactic dynamo possibly fill the immense cosmic voids? This suggests that the seeding of magnetic fields might have occurred on a truly universal scale before galaxies ever formed. The fields we see today might be primordial, a fossil relic from the universe's first moments, stretched and woven by cosmic expansion into the web we now detect. Their silent, pervasive presence is a ghostly reminder that the early universe was a far more dynamic and complex place than we can yet comprehend. The silent, magnetic cosmos seems to operate on autopilot, governed by impersonal laws. Yet here we are, a part of that cosmos, consciously experiencing it. This brings us to the most intimate and perplexing mystery of all. How does consciousness relate to the expansion of the universe? We are not just passive observers of the cosmic drama. We are the universe itself, become self-aware. The very atoms that form our brains were forged in the hearts of long-dead stars, and now they are arranged in a way that allows them to contemplate their own origin. This is the hard problem of consciousness. We can map a brain, understand its neurons and synapses, but we cannot explain why or how this intricate physical processing gives rise to the inner, subjective experience of the color red, the taste of salt, or the feeling of wonder. It is the one piece of the cosmic puzzle that is not out there in the distant galaxies, but right here, inside our own minds. Is our consciousness merely a random, accidental byproduct of a universe that expanded in just the right way to eventually form complex brains? Or is it somehow fundamental, woven into the fabric of reality from the very beginning? Some physicists and philosophers entertain a radical idea known as panpsychism. This is the view that consciousness is not something that magically emerges only at a certain level of biological complexity. Instead, it is a basic property of the universe, as fundamental as space, time, and matter. In this view, even an electron might possess a minuscule spark of proto-consciousness, a tiny inner experience. When these simple conscious entities combine in systems of immense complexity, like a human brain, they give rise to the rich, unified consciousness we experience. If this is true, then the universe was not just set up to create galaxies and stars, but was inherently predisposed to awaken. The expansion, the flatness, the precise values of the constants, all of it created the necessary stage for a cosmic mind to eventually emerge and reflect upon itself. This feels like a profound form of fine-tuning, as if the laws of physics were designed with consciousness as a goal. The alternative is that we are a magnificent cosmic accident. In an infinite multiverse, with countless bubble universes governed by different physical laws, it is statistically inevitable that at least one universe would have the perfect conditions for life and consciousness to randomly arise. We just happen to live in that one. There is no deeper meaning or purpose. Our awareness is a beautiful, fleeting fluke in an otherwise unconscious and mechanical cosmos. The expansion of the universe, in this view, is simply a physical process that accidentally created a niche where self-reflection could occur. The truth is, we have no idea which view is correct. Consciousness remains the one thing we cannot observe from the outside, the one phenomenon that resists all our standard scientific tools. The universe expanded for billions of years in darkness, and then, in a tiny, recent flicker of cosmic time, it suddenly began to shine with light and wonder itself. Was this the point all along, or are we just a brief, curious echo in the vast, indifferent dark? Our conscious observation of a fine-tuned cosmos rests on one final, monumental assumption. We take for granted that the laws of physics are universal and unchanging, the same immutable rules from one end of our observable bubble to the other. But what if the rulebook itself is not consistent? The ultimate answer to the fine-tuning problem may be that there is no fine-tuning at all. In an eternally inflating multiverse, the fundamental constants and even the laws themselves could be different in each isolated bubble universe. The strength of gravity, the mass of an electron, the value of dark energy, these are not written in stone for the entire cosmos. They are merely the local bylaws of our particular cosmic neighborhood, determined by the random way our pocket of space stopped inflating. We do not live in a universe perfectly engineered for life. We live in the one universe out of an unimaginable multitude, where the numbers just happen to fall into the narrow range that allows for galaxies, stars, planets, and conscious beings to exist. This idea, known as the anthropic principle, is not an explanation in itself, but a selection effect. Imagine a vast lottery with countless losing tickets, each representing a universe where the constants are wrong. In some, gravity is too strong, causing stars to burn out in a flash. In others, the nuclear forces are too weak, so atoms never form. In many, dark energy is so potent that it rips apart any nascent structures before they can even begin. We could not possibly find ourselves in any of those barren, lifeless worlds. Our very existence as observers automatically selects for the rare, winning ticket, the one universe where the numbers allow for our presence. This resolves the fine-tuning problem not with the designer, but with a cosmic numbers game. The multiverse provides the lottery machine, churning out every possible combination of physical laws. Our universe is not special. It is simply survivable. The profound silence we encounter when we look out at the cosmos might then be the most telling evidence of all. It suggests that the conditions for complex, intelligent life are not just rare on planets, but incredibly rare across the entire landscape of possible universes. We are not just alone in our galaxy, we may be alone in a vast, mostly lifeless archipelago of realities. The final, haunting question is not why our universe is so perfectly tuned for life, but why we are here to notice it at all. A single flicker of awareness in an infinite, indifferent cosmic sea. From the ghostly push of dark energy to the silent architecture of dark matter, our journey through these 25 questions reveals a cosmos far stranger than we ever dreamed. The simple fact that the universe is expanding has ripped open the fabric of our understanding, exposing profound mysteries at every scale. We are left grappling with the true nature of reality, from the possibility of a holographic universe to the illusion of time itself. The unsettling quiet of the Fermi paradox and the fine-tuning of our physical laws force us to confront our own place in this vast, and perhaps infinite, cosmic arena. These are not just academic puzzles. They are the bleeding edge of human knowledge, the frontier where our most brilliant theories meet the hard wall of the unknown. Each question is a doorway to a deeper level of reality, and every answer we seek seems to reveal two new, more profound mysteries in its place. The expanding cosmos is a Pandora's box, and we have only just lifted the lid. So we turn this final question over to you. Which of these cosmic enigmas keeps you awake at night, staring at the starry sky? Is it the haunting silence of alien civilizations, the terrifying potential of a big rip, or the mind-bending possibility that our entire reality is a projection from a distant boundary? Share your thoughts, and never stop looking up with wonder. The greatest discoveries are still waiting, hidden in the dark between the stars.